Broadcast is now starting. All attendees are in listen-only mode.
Hello everyone and welcome to GridGain Systems webinar, How to Make a Backup in a Distributed Systems Unnoticed. I'm Nicole Vangelua and will be today's moderator. Before starting, I will need to conduct a little housekeeping. Can you raise your hand with the hand icon if you can hear me? Right, I see some hands, so we are good to go. On behalf of today's webinar's presenter, thank you for joining us. I'd like to introduce our speaker for today. Ivan Rakov is a senior software engineer at GridGain. His focus is on Apache Ignite. If at any point during the webinar you have a question, please type it in the Q&A panel. Questions will be addressed at the end of the webinar. Please also note that your phones will be muted throughout the presentation. You've joined us today to hear about how to make a backup in a distributed systems unnoticed. At the end of the webinar, we'll close out by taking your questions. With that, I'd like to now turn things over to our expert, Ivan Rakov.
Hello everyone, I'm Ivan and today I will tell you how to make a snapshot in a distributed system unnoticed. Basically, my presentation will cover internal mechanics of how to make a snapshot in a distributed system. I will cover difficulties of this procedure, and if you are interested in using GridGain and making snapshots in GridGain, I hope that my presentation will make the whole process more clear to you. Okay, let's get started, and let's start with a brief introduction what is Apache Ignite and GridGain is, and in which system we have implemented backups. Speaking shortly, Apache Ignite is open source distributed RDBMS. It's also caching and computation platform. It can be used in mostly two ways. It can be a separate database or a cache for a third-party storage. I'm sorry, just a moment. Okay, let's go on. The key features of Apache Ignite is simple data partitioning. It's really easy to partition and distribute your data among the cluster. All your entries will be separated into atomic units called partitions, and you can specify an affinity function which will decide where every partition will be stored. So when you change your topology, partitions are simply moved from one node to another in background. Also, there are distributed transactions in Apache Ignite. It's fully ACID compliant transactions. You may specify any isolation level you want and gain all the transactional guarantees. Also, Ignite has affinity collocation. It's ability to send your computations close to data. When you partition your data based on some predicate or some key, for example, by city, if you want to compute some analytics for specific city, you can just write affinity run or affinity call, and Ignite will automatically send your computation to your city. GridGain is an enterprise-level solution for systems based on Apache Ignite, and also GridGain Systems is a major contributor to Apache Ignite. Nearly half of the commuters in Apache Ignite are GridGain employees, but GridGain is not only one force in Apache Ignite project. A few words about myself. I am senior software engineer at GridGain Systems. I'm also a committer in Apache Ignite project, and I have participated in Snapshots implementation in GridGain, and that's what I'm going to tell you about today. Let's start with the agenda of today's webinar. Firstly, we'll discuss what's wrong with the distributed snapshots, why making snapshot in distributed system is not so easy. Then we'll go on and discuss a simple solution that can be implemented in any distributed system with persistence through cluster shutdown or deactivation. Then we'll continue and achieve creating snapshots concurrently under user load. We'll firstly discuss how to achieve local consistency. By local consistency, I mean consistency of all data and data structures on one node. Then we'll discuss how to achieve global consistency. We'll cover a topic how to save your space and performance and create incremental snapshots. And at last, we'll discuss what to do if your topology changes, how to use old snapshots created on old topology. Let's start with the problematics of this topic. What's wrong with the distributed snapshots? First of all, it's not actual only for distributed systems, but for all databases as well. Data gets constantly updated, and when you create a snapshot, you want to create a snapshot for a certain timestamp. Snapshot creation may take several hours, and you want all data in your snapshot frozen at the state for some moment. Amount of data may be really large in distributed snapshot. What does it mean? When people use distributed systems, they can do it for two reasons or for both of them at the same time. Either one machine can't handle all the loads that your system needs to handle, or you have so much data that can't be effectively stored in one physical machine. Anyway, amount of data may be really large, and this makes urgency of creating snapshots in backgrounds even more higher, because when your snapshot creation takes a really long time, it's extremely critical to continue operating even when snapshot is getting created. Data is replicated in distributed systems. It's a usual mechanics. How do distributed systems protect themselves from data loss? They just store data, in our case, data partitions, in multiple copies. In Ignite configuration, you can specify backup count, its number of partitions that will be also stored in your cluster except primary partition. And when you create a snapshot, you probably want to all copies of your partitions to be equal. You don't want the data be inconsistent between replicas of your partitions. Here we add transactional consistency. When users implement transactions over Ignite, they do it for some reason. They want to achieve some kind of transactional guarantees. The classic example is a wire transfer between two bank accounts. When you transfer money from one account to another, you want the total sum of all money to be unchanged. And also, when you create a backup, you want total sum in your backup to be the same. So backup should be transactional and ACID compliant. Also, there may be conflicting changes in cluster. Imagine that you want to change something in your cluster, for example, change DB schema, add any kind of table, or add index and whatsoever. The point is that such operations must be ordered with snapshot creation. Otherwise, these changes may appear in snapshot in not atomic way. Newly created table may appear in one nodes in snapshot and don't in another nodes, and this would be a disaster in terms of cluster consistency. And at last, what we have already mentioned is that cluster topology may change. You may create a snapshot at one set of nodes, then your cluster may grow. Some of initial nodes may leave, and you still have to handle all the backups. You still have to be able to restore snapshot created on old topology over the new topology. Well, let's start with a brief overview of existing approaches in existing distributed systems. Some database vendors don't provide an option to create a snapshot under load. They suggest to perform a cluster shutdown and then run a command to create a snapshot. This approach is good to go unless there are requirements in your system that it should operate 24 hours and 7 days. In such case, you can just shut down the cluster and you have to find another approach. Some distributed systems vendors like Apache Cassandra suggest to take an eventually consistent snapshot. I'll describe what does it mean. Cassandra has an internal mechanism of eventually consistency. It also stores data in several copies, and data may be different between the copies, but consistency is still not broken because Cassandra has internal repair reads mechanism. So when you create a snapshot in Cassandra, several different versions of partitions may appear into the snapshot, but it's still okay because after the restore, inconsistencies between partitions will be fixed according to repair reads. What's the problem with this approach is when you have to handle transactions. Keeping an eventual consistency becomes way more difficult. I have to say that Cassandra also provides transactions, and a consistency provided by these transactions is not broken in Snapshot. But I also have to say that Cassandra provides lightweight transactions. That means that you can modify only one entry in each transaction. Basically, it is equivalent to compare and set operation. When you perform more difficult transactions that take into account several keys or even several data tables, it becomes way more harder to maintain an eventual consistency. And that's why such approach turned to be inapplicable in our system. I also have to say that transactional consistency was never a key benefit of systems like Apache Cassandra. Transactional consistency is something from the world of SQL bases, and there is a bit famous distributed SQL database as CockroachDB, and it also provides an option to create a transactional consistent snapshot using such feature is MVCC. MVCC is a multi-version concurrency control. Speaking shortly, it's a feature that allows to increase concurrency level in your system, allows to perform reads and writes on some keys, probably the same in concurrent manner. But cost for this is extra overhead. MVCC uses global versioning of transactions. Every transaction that starts has a version, and every version in cluster can be compared with another version. There's a strict order between all versions, and the data is stored in several instances, and all the instances gets cleaned in background. So if you modify your key very often, you may accumulate several versions of your engine. And that's how MVCC works. When you want to create a read consistent view of all data, you just fix the version. And with that version, you iterate over your data rows and get rid of rows which has older version. And that's how Snapshot can be created in MVCC system. In one way, you can just copy all your data, including old versions, into the snapshot, but in this way, you will have memory overhead, because in case of high loads, amounts of extra versions that are redundant but still copied may be high. You may do it in another way. You can just iterate over all your data and only copy versions that are higher than fixed version. But in such case, your snapshot creation will be slower, because just bulk copying of all your data on file system level is way more faster than iterating over your data and executing some code. And the another reason why we didn't use this approach in our system, because there was no MVCC. I want to mention that MVCC is going to be released in closest Apache Ignite release 2.7, but we needed snapshots way more earlier. Okay, let's start with the simple solution. I'll tell you how to achieve a snapshot in any system with deactivation. It may be obvious, but let's pass through it to get started. Imagine a cluster of distributed systems. There are several nodes. Each node has a disk storage, and on each node there are partitions with data. Numbers on the in squares on the clouds are partition numbers. And by definition, persistent means recoverable from disk. So in order to achieve a snapshot, you can just deactivate your cluster. Apache Ignite provides such option. And during the deactivation, all user load will be stopped and all data will be dumped to the disk storage. And at this point, if you will start your cluster, it will recover its state. So in order to achieve a snapshot, you can just take your disk storage and just copy it to the separate directory. And in case you need a restore, you can just perform a reverse operation. You can deactivate your cluster and replace your disk storage with the previously stored disk storage from snapshot directory. This approach makes sense, but it has an obvious cons. It has a downtime. It's not always a good approach when you need an unstoppable system. Well, let's discuss how to achieve snapshot creation under load without system stop and without downtime. Firstly, we need to establish local consistency. Let's discuss how modern distributed systems use or databases achieve local consistency in checkpoint or in snapshot. To get locally consistent state, Redis, for example, does fork of its process, and in Redis continues load on the one sibling of process, and from another sibling it just iterates over all data and dumps it into the snapshot. What's the cost approach? First of all, you need to stop all your threads for a bit. You need to achieve kind of stop the world, and otherwise state of threads is not guaranteed in forked process. And even if you will stop all your threads, fork itself requires some time. Operational system needs some time to initialize data structures and so on in forked process. And it requires time. It requires from 10 to 100 milliseconds per gigabyte of memory process. That means if you have a node in cluster that uses 100 gigabytes of RAM, you need to freeze your activity for 1 second. We have deployments the over 700 gigabytes of RAM per each node, so this makes this approach inapplicable at all. And most of all, you also have memory overhead in fork. Operational system performs copy on write to maintain different states of two processes, and in worst case, you will require to allocate the whole pool of memory of all process. So basically, your memory consumption will be doubled, and you may just get an allocation failure, or you have to preserve a lot of RAM free. The other approach, which is performed by modern databases, is fuzzy checkpointing and analyzing redo log or write-ahead log or undo log. Basically, checkpoint is the process of dumping accumulated changes to the disk, and fuzzy checkpoint is the most modern approach that can be used. It can be performed without any kind of stop. You may still perform full load and take a fuzzy checkpoint. I need to say that fuzzy checkpoint is quite a complex algorithm. It's not such complex itself, but you have to make your data structures consistent in some way to be prepared to fuzzy checkpoint. Challenges that are faced by modern databases are quite different from challenges that faced by distributed systems. The only way to achieve the best performance as possible in database is to use as efficient algorithms as you can. And when you have a distributed systems, you can just scale, you can just add more nodes to handle higher load. That's why we used a bit more simple algorithm of sharp checkpoint. I think it's quite understandable, and it also helps us to create a snapshot. I will tell you about it later. And I'll cover what is sharp checkpoints in 5 minutes. Okay, to understand what is sharp checkpoint, let's get started with how Ignite stores its memory on the RAM and in disk. Ignite stores all its data into pages, and pages are always stored on disk, and optionally pages are also stored in RAM. It's kind of caching. It's also what allows Ignite to achieve high performance along with the persistence, and only some hot subset of your pages is stored in RAM. And when you update the pages with the user operations, the pages get dirty. What does it mean? We store dirty flag, dirty is true, and just accumulate such dirty pages in RAM. And when amount of dirty pages gets really high or there is a timeout, we just write all dirty pages to the disk in batch mode. Writing in batch mode is way more efficient than writing pages one by one. And this process is called checkpoint. Checkpoint is writing a batch of dirty pages to the disk. But checkpoint also needs to be consistent. And there are two questions that we face. First is how to maintain atomicity. By atomicity, I mean that complex operations should either be included in checkpoint completely or not included at all. Imagine an entry update that updates a big data row that can't be fit in one page. It updates 2 pages, and when there's a user operation that updates 2 pages, it's undesirable that such operation would be partly included in checkpoint. So if we will start checkpoint in the middle of such operation, the first page will get into checkpoint and the other page will not get into checkpoint. And we should avoid such situation. The other problem is concurrent updating. When you write a checkpoint, you want to write a state for a fixed timestamp, and there is a possibility that user threads will come and modify pages which are not written to the checkpoint yet. We would have to block the user loads until we would finish writing checkpoint, but we don't do this way. We have handled this problem, and I'll tell you how. Okay, we use such approach as checkpoint read-write lock. Read-write lock is analog for shared or exclusive lock. We take a read lock for every update. So when user starts transaction, it's finally reaches a node with the data, and it acquires checkpoint read lock in order to perform an update and make pages dirty. And when we start a checkpoint, we acquire a write lock. When you have successfully acquired write lock, that means that no one is holding read lock. And when the write lock is acquired, we just take a snapshot of dirty pages. We just accumulate all dirty pages, not only in flags, but in some collection. And under checkpoint write lock, we just take snapshot of this collection, and then we release write lock and just continue writing, continue user transactions to acquire read locks. Okay, now we have fixed collection of checkpoint pages, and what will we do with it next? There is a checkpoint thread, and checkpoint thread iterates over dirty pages collection and cleans the dirty flags. Thread writes a page and cleans dirty flag for it. There may be a case when there will be new updates, and if a user transaction will update a clean page and make it dirty, such update will get into the next checkpoint. We can simply achieve it because we have prepared and snapshotted collection of dirty pages, and it will be not modified in the progress of checkpoint. The another problem are concurrent updates. User transaction may update a page, for example, this one, and this page is not written yet to the checkpoint. To resolve the problem, we perform copy on write. We have allocated a separate buffer for such pages. It's called a checkpoint buffer. And by the way, you can even configure its size. But it's not mandatory. There's a throttling mechanism that prevents checkpoint buffer from overflow. So when user transaction comes and it understands that it has to modify a dirty page that wasn't checkpointed yet, it just copies its old state into the checkpoint buffer. Old state will live here and writes over its new state. And checkpoint thread will take these old states into the account. It will reach the checkpoint buffer and clean it. It will take a page from buffer, write it to the disk instead of the actual page. And at the end of checkpoints, the checkpoint buffer will be completely clean. Okay, with these two approaches, we now can write dirty pages to disk with consistency maintained, thanks to the read-write locking, and with concurrent load, thanks to checkpoint buffer and copy on write. But that's not enough. We now can write only dirty pages, and the question is, can we write not only dirty, but all pages with the same guarantees? The answer is, of course, yes. And that's how we achieve it. So task is to write all pages to the snapshot directory with all these guarantees, with atomicity and under concurrent load. To make this possible, let's create an entity which is called snapshot checkpoint. Snapshot checkpoint is not a term from any technical literature. I'll just name it this way, and I will reference a snapshot checkpoint a few more times during the presentation. So during snapshot checkpoint, it consists of two parts. During the first part, we perform a usual checkpoint, but we write pages into two destinations. We write pages to the disk storage, like we do during a regular checkpoint, and we also write pages to the snapshot storage. And in the end, all pages will appear both in disk storage and also in snapshot storage. That's not enough. There are also pages that were clean at the moment of checkpoint, and we need to write these pages. We will just scan disk storage to write remaining pages. This sounds very simple, but there may be problems with that because we also have a concurrent load, and next checkpoints may concurrently update disk storage. So when we start a snapshot checkpoint, first phase is conjoined with the actual checkpoint, and after the first phase finished and we do the second phase, which includes writing the remaining pages, another checkpoints which are not snapshot checkpoints may start, and we have to handle it. We have to allow regular checkpoints to work concurrently with the snapshot creation. Next checkpoints may concurrently update disk storage, and you may feel a deja vu sense because we already faced this problem a few slides ago and we have already solved it. To maintain snapshot writing under concurrent load, let's discuss how it's implemented. There is a snapshot thread that scans disk storage and write TBD pages. TBD pages are pages that were clean at the moment of checkpoint. And in case next checkpoint has come and it's going to update page that is not written yet, we'll just force it to write old state of the page to the snapshot. It's nearly simple and it looks like approximately as copy on write that we implemented in checkpoint, but now we do it in a bit another way. We don't use in-memory buffer, we just force checkpoint thread to perform an extra work. It performs a cooperative write to snapshot. So basically it's the same copy on write and it's just performed synchronously. So let's compare it with the previous approach. before, when we did checkpoint, we read from memory, we wrote to disk. The factor that we have to deal with was concurrent data updates, and we use checkpoint buffer to maintain a copy on write. Now, in this second phase of snapshot checkpoint, we read disk and write to snapshot storage. Concurrent factor is next checkpoints, and we use cooperative multi-threading to maintain copy on write. And now we have created an algorithm that allows to dump a consistent state of all pages on the node and do it under load. That's good, but not good enough. We still have to reach global consistency. And to start discussing global consistency, I'll first enlighten typical problems that distributed systems may face. And first of all, let's dream a bit. If only we could make cluster consistent for at least 1 millisecond. If that would be possible, we'll just initiate a snapshot checkpoint in this time window, and the result will be globally consistent snapshot. Sounds good, but we have to make cluster consistent for 1 millisecond, which is not so simple. And let's consider a part of life of typical distributed system. And what may happen? What may go wrong? What are typical issues of distributed systems? Imagine that there are administrator that decided that he wants to add a new table. He enters the command to add new table on one node, and the node starts propagating this command across the whole cluster. And there is another conflicting administrator, and that conflicting administrator decides to create a snapshot. He also enters command on another node, and another node starts propagating this command to the whole cluster. And we may bump into the situation when several nodes will obtain these commands in different order. There will be nodes that will firstly accept command to create snapshot, and there also will be nodes that firstly will accept command to create table. And to make picture complete, some node should just crash and make the situation even worse. Yes, and the result of this scenario will be a complete mess. And what can be a conclusion for such story? There is a Russian fable about crowfish, swan, and pike. And there was a wagon, and they were dragging the wagon into different directions with the high efforts. And they were blaming each other for the failure. And as you can guess, the wagon just stood still, and it wasn't moved for even a bit. And the conclusion is that failover scenarios can be handled, but it's quite complex to make it correctly. And the more simple solution is to make such global events as new table creation and snapshot creation ordered. If all nodes would accept such operation in strict order, there would be no problems with consistency. And how it is achieved in Ignite? There is a ring topology in Ignite. Nodes ordered by the time of appearance in the ring. First node is first in ring, and it has discovery connection to the next node. If we maintain such ring, it's easily to reach consensus of who is the leader or coordinator. We can just assign a coordinator role to the oldest node in the ring. And once we have consensus and strict node ordering and one connection, one pipe in which messages are transferred through the ring, we may easily order global events. How do we do it? When one node wants to trigger global event, it just sends a message about global event across the ring. Message is sent, and if in case messages can surpass one another in the ring, so coordinator will coordinator will get these messages in some order, and coordinator will validate the messages and send them in the order in which he has received these messages. So there's one pipe, messages order can change in this pipe, and if the coordinator sends new table message first and then snapshot message, all nodes will reach all nodes will receive these messages in the same order. And this basically solves our problem. If the global events are ordered by coordinator and sent through the ring, all nodes will receive them in the same order, and there will be no mess. And how this option to use ring and order the events may help us in building a globally consistent window. Let's discuss how it is performed in Ignite. In order to build a globally consistent window, the initiator passes message about window creation, passes it to the ring, messages reach coordinator, and then validated and reaches every node. And we also, again, perform read-write locking. There is such thing as topology read lock, and every user transaction that wants to get started and modify anything acquires topology read lock. And when we send such message, and when every node receives it, every node starts acquiring topology write lock, and for some after some moments, write lock is successfully acquired. And acquiring write lock means blocking of all new updates, because no one holds a read lock, and if someone wants to do update, he has to acquire read lock. In such case, when topology write lock is acquired everywhere, actually it's consistent state, and every node can send ACK about successfully locked topology to the coordinator. Coordinator will await all ACKs and will broadcast messages about, okay, job is done, you may now perform a write lock and continue accepting user transactions. It's easy to perform because there is a consensus which knows coordinator. And with such approach, we have a window in which actually cluster is globally consistent. In the details, so what we have to do is just run snapshot checkpoint in the window on every node. And a good moment to start it is after successful acquiring of topology write lock and before sending ACK to the coordinator. If every node will perform it that way, the snapshot checkpoints across the whole cluster will be consistent between each other. Well, now we can take snapshots which are local and globally consistent, but we still have some issues. First of them is that snapshots really take a lot of space, and we'll discuss how to save the space using incremental snapshots. Okay, let's discuss how snapshots are usually created in practice. Snapshot creation is usually scheduled on a daily basis, for example, at the morning, once a day. And in practice, data can be separated on operational and historical data set. What does it mean? Most of data are historical and it's changed very rarely. And some small amount of data is operational and it's changed regularly. For example, when you have accounting system, current state of accounts is operational data set, and story and history of account actions is historical. So the point is that the same set of historical data is saved in Snapshot every day. And that's not good. We again and again save the same historical data. We might want to get rid of it in order to save space. And how can we achieve it? Data is stored in pages, and we can just compare pages. When we write a snapshot, we can compare current state of the page with the state from previous snapshot. And we can write page only if it differs. This will bring us a first approximation to incremental snapshot. This is a good approach, but the problem is that we want to make snapshot creation more performant and quick. And in such scenario, we still consume the same amount of I/O operations. When we create a full snapshot, we spend 100% of I/O operations for writing pages to the snapshot. And when we perform such incremental snapshot, we save write I/O operations because we write only operational data set. It's, for example, 10%. But we still have to read 100% of pages from the previous snapshot in order to understand whether or not should we write page to the incremental snapshot. And we still consume a lot of I/O operations. We may work this around, and we did it by using tracking pages. We added a new separate page type for storing bit masks. Every page has a type, and tracking page is auxiliary page type, which is used for internal operations. And in bitmasks, tracking page covers a range of regular pages. In current implementation, for one tracking page, there's 16,000 of regular pages. And we store 1 if page was changed since previous snapshot, or 0 if it wasn't. Okay, sounds good, but there's a problem. How to write a snapshot and collect data for next snapshot at the same time? Because when we start snapshot creation, we will read over these bit masks in order to understand which pages we have to write. And we also have to let user transactions change pages, and to it will change bit mask. And the problem that we have to read a frozen state of bit masks and change it at the same time. How to do it in one bit mask? Speaking shortly, there's no answer for this question, and we just store 2 bit masks. 1 bit mask is for current snapshot, and 1 bit mask is for next snapshot. And what we do is when data update comes, we change a bit in next snapshot bit mask. And when operation of incremental snapshot creation starts, we invert these 2 bit masks. We don't actually invert them in every page. We just save a global tag and we just increment it. And odd tags means that next part is right, and even tags means that next part is left. We just change tag on incremental snapshot. Masks are swapped, and we perform a lazy zeroing of the mask. Imagine that we have started incremental snapshot creation and we have swapped the masks, and then new update comes. It understands that the mask is lazily zeroed because its internal tag differs from the actual most recent tag. And in such case, we just perform actual zeroing, and we put 1 on the spot of the firstly updated page. So we accumulate changes in such masks, we swap them from time to time, and we read from them when we have to create a snapshot. And using such approach, we have implemented an incremental snapshots, and it's actually saves your space, and they are way more performant than basic snapshot. So you have to consume our the way less IO operations when you create an incremental snapshot. Okay, and the last topic is that topology may change, and how can we use old snapshots? Let's consider a scenario when there's a cluster, and the snapshot was created on the cluster. And after that, after a couple of months, topology of cluster was changed. Some nodes were sent to the maintenance, and instead of them, some new nodes were added. And distribution of partitions may have changed, and snapshot that was taken 2 months ago went away on the left node. So some nodes that survived contain that snapshot, and some parts of snapshot are lost forever. And how to restore this partly saved snapshot? It's hard to say, and it's also a problem that storing snapshots locally is not efficient because you do it quite often, and disk space is limited on your local nodes. And that's why we have implemented a move command. When you and after you have created a snapshot, you can simply execute a move command, which allows to move all your saved snapshot data to some network storage to shared folder. You just execute this command in command line. You just type path to the shared folder, and your snapshot gets moved and gets deleted. And how to use, so the results of the separation is a snapshot which is fully contained on the network storage. And then when your topology has changed, in order to restore snapshot from shared folder to the new topology with new partition distribution, we just restore snapshot by current distribution. What does it mean? New cluster knows about its partition distribution. He knows where which partitions should be placed, and we also stored partition distribution of old cluster in snapshot metadata. So there is metadata which can be read by every node, and every node may understand where it can find its partitions in the snapshot directory. So what is need to be done by each node? Each node should read the metadata and find its partitions across the folders from different nodes, probably in the snapshot directory, and just copy these partitions to local disk storage, and then just perform restore. Partition is a minimal atomic unit of information transfer in cluster. The partitions are moved from one node to another when we change partition distribution in cluster, when we want to scale. And the same operation is performed during distributed restore. We just move this partition from storage to the local nodes. That sounds okay. And the benefit is that snapshot from network storage can be restored on any topology. And the cons are that some entities are not partition local, but node local. For example, for several reasons, we build our SQL indexes in per node way. SQL index on the node contains links, and it's indexed over all partitions that are locally preserved on the node. And the disadvantage of this approach is that when we restore a snapshot from network storage and the partition distribution have changed, we have to rebuild SQL indexes. That means that right after restore, your system will be operating, but its performance will be decreased for SQL queries. And then when the SQL indexes will be finally rebuilt, it's performed in asynchronous manner. Everything will be okay. Your indexes switched on, and your performance will return to the normal value. Such operation is mandatory only when partition distribution was changed. If it wasn't changed and snapshot was moved, SQL indexes will be restored along with the partitions. So we have covered the topic what to do with old snapshots in case your topology was changed. You have just to maintain a network storage and store your snapshots in that storage. So that's all I wanted to tell you today. Thanks for your attention, and now I'm ready to answer any questions.
Thank you so much, Ivan. I would like to give you the opportunity to ask your question to our expert. Type your questions in the Q&A panel now. I see that we have received a couple of questions already. You have mentioned consensus. What consensus algorithm is used in Ignite?
There are several approaches in Ignite. There is such thing as discovery SPI, and you can configure. There are two implementations. There's TCP discovery SPI and Zookeeper discovery SPI. And when the default implementation is TCP, and it's actually the ring that I told you at the middle of the presentation. It's our own consensus algorithm. It has no formal proof, but it's served for many years in production, and it shows good performance for the cases when clusters are not too big. If your cluster is big, I mean bigger than 100 of nodes, and you want to use formally proved consensus algorithm, you can specify a Zookeeper discovery SPI, and in such modes, Ignite delegates work by reaching consensus to the Zookeeper cluster. And in Zookeeper, there is the ZEB algorithm used. Zookeeper was created way before that Raft papers were published, so it's algorithm nearly close to Raft in one way or another.
Thank you. And the next question we have is, how will background snapshot creation affect performance of GridGain cluster?
Okay, we have, when we were discussing snapshot, we discussed that snapshot checkpoint does more work than usual checkpoint. Usual checkpoint writes pages to only one place, and snapshot checkpoint writes pages into two places, into the disk storage and into the snapshot directory. And when you use persistence, throughput of your system is bounded with the speed of checkpoint. One way or another, all your changes should be checkpointed. So the answer to your question is, in worst case, total throughput of your system during background snapshot creation will be decreased twice. So you will gain only half of your regular throughput. And that's the reason why it's better to take snapshots in non-active hours. But when the first phase is finished, you will return to your normal throughput, and during second phase, throughput will only be decreased if there will be concurrent load. So if there were pages that were concurrently updated by next checkpoints, your checkpoint, your maximum throughput will float between half and maximum throughput.
Thank you. We reached the top of the hour, so we have no further time for questions. So I would like to thank our speaker today, and also thank you for each of you for joining us and for your participation. Thank you and have a wonderful day.
Thank you, Nicole. It was a pleasure to discuss such matters.
Thank you.